Okay, let's go ahead and get started. Today what we want to do is continue our discussion of the stars. Since we now know the distances to the stars, or at least a method to find the distance, there's a bunch of stuff we can now learn about the stars that we couldn't know before we knew the distances. And just as a reminder, after we climbed up that distance ladder from determining the size of the Earth to the size of the Moon to the distance to the Sun, we could use a process called parallax to figure out the distance to the nearby stars. So what I've got here is a little demonstration of parallax. And one of the most important things about parallax is that the amount of shift you see is dependent on the distance the star is away. So here I've got a star at 1 light year, and you can see this little red star bouncing back and forth. If I move this out to 5 light years, it bounces back and forth a little bit less. If I move it back to 10 light years, it bounces even less, and if I go out to the full 20 light years, I can hardly see any motion at all. And the reason that we have that limit is it's fixed by the size of the Earth's orbit, because we look at these stars at 2 times per year, June and January, and if they're too far away, we can't see their distance. So we can't use parallax to determine the distance to all of the stars in the galaxy, but we can determine the distance to enough of the stars to learn about the properties of stars as a kind of a statistical sample. So that's what we're going to talk about today. I do want to point out that in one of your activities for the parallax, it talked about how we might improve this situation, and you were asked to look at different scenarios. Best that we can do with parallax right now is putting something in orbit around the Earth. That gives us the same baseline, so it doesn't get us to any further distance, but it removes some of the atmospheric distortions that would get in the way of our observations. Anyway, if we increase the baseline to Pluto's orbit, we could get an increase of about a factor of 40, because Pluto is about 40 astronomical units away. That would be great, except we'd have to wait 200 years for the observations, because that's how long Pluto's orbit is. So we really kind of are in the best possible situation. We only have to wait a year between observations, and we can get out to a pretty large statistical sample. What we'll find is we can use the information about stars in order to determine distances in lots of different ways. Okay. So let's go back to our presentation here. And again, I'm sitting here looking at a collection of stars that have different colors. And we know from previous conversations that the color tells you the temperature. But it doesn't tell you anything about how bright they are just by looking at it. Let's take a look at a star. If you've got a star that's intrinsically bright but far away, it could be quite dim. And the reason for that is because the energy that that comes out of the star as it shines is distributed over a larger area as it expands away from the star. So you can imagine, if you have a light bulb in your room, the closer you are to the light bulb, the brighter it looks. And that's just because the energy coming out that light bulb is distributed over a smaller area. And since area goes like the square of the distance away from the object, if we imagine a spherical distribution of energy, the farther away you go, the dimmer the light appears, and it drops in brightness by the radius squared. So if I'm twice as far away, that means I'm 4 times dimmer. If I'm 3 times as far away, it means I'm 9 times dimmer. And that's what this is illustrating here with these little boxes, that if I happen to be close to the star at 1 astronomical unit, then all of the energy in this box is hitting this area here. But if I go out, that same amount of energy gets distributed over a larger area. So now if I'm out here, the area is 4 of those boxes. And if I continue going out like this, the area is 3 of those boxes, or 9 of those boxes. Right? So it goes out like the distance squared. So that just means that if you're sitting here with a detector at one of these boxes, you're measuring 1/9 of the radiation in that little box. That's handy, though, because that means if we look at a star and we look at its brightness, if we know its distance, we can tell how bright it really is by comparing how bright it appears to how bright it really is from its measurements. What are the ranges of these luminosities? When we go out and look at this statistical sample of stars that we know the distances to, there's a huge range. So the sun, if we imagine the luminosity of the sun to be 1 unit, so we just say the sun is as bright as the sun, there are stars out there that are 1,000,000 times brighter than the sun. There are also stars out there that are 1/10,000th the brightness of the sun. And this is where you probably heard people say the sun is an average star. The reason for that is because the sun is roughly halfway between the two extremes in luminosity. Now, it turns out the sun is not average in number. It's not the most common type of star. The most common type of star are red dwarf stars, which we'll talk about a little bit later. And those are the very, very dim stars. So these are the most common stars. These are common. And these guys are rare. And the sun is kind of halfway in between at 1 solar luminosity. And it's relatively rare. It's not as common as other stars in the galaxy. But because we have these distances, we can measure those ranges. So that's a piece of information we didn't know before, what the range of brightnesses of stars are. Now, we've talked about temperature. If we have a brightness for a given star, we can figure out its temperature by looking at its color. And then we have two intrinsic properties that we can compare together, the luminosity and the temperature of these stars. So you'll recall that for temperature, what we do is we look to see how the color changes depending on the temperature. If you have something that's really hot, it goes from blue to white hot, and if you have something that's very cool, it's reddish in color. And that's just because of the thermal radiation that's emitted. And this is something we talked about earlier with continuous emission. And these are what those continuous spectra look like. So again, if I've got imagine our visible wavelength of light, what we're looking at here is a rainbow. This is what your eye can see right here. This is your typical Roy G. Biv rainbow that your eye can see. So if we break this up into its spectral components, stars with different temperatures will cross that visible range that we can see in different ways. And when we see a color, what we're seeing is more of some radiation than the others. So for example, in this 15,000 Kelvin star, there's a lot more blue radiation coming out than red radiation. So we're going to see that as a blue object. The sun, which we call it a yellow star. It's really white. The yellow comes from the fact that the blue gets scattered out in our atmosphere, but it's a yellow-white star, and that's because it pretty much has even amounts of all the colors right there. And then a red star down here, this 33,000 Kelvin star, this red star, has more red radiation than blue radiation, so it looks red. So you're detecting basically changes in slope of the radiation as it cuts through your visible spectrum of your eye. And you also emit a continuous radiation. This is a human down here with a body temperature of about 310 Kelvin, and you're down here in the infrared. So we can't see the visible radiation from your body, but we can feel it in the form of heat. And it's the same sort of radiation that would come out of a star. It's just you happen to be much, much, much colder than a star, so your radiation comes out in the infrared. So again, we can tell the color of stars just by looking at them, and since we can measure their color, we can measure their temperature. The relationship here is that as the star increases in temperature, this peak just moves to the left in this diagram. And the further to the left the peak is, the hotter the star is. So again, we can measure all the stars in our statistical sample that we know the distances to, and we find some stars that are typically rare do have temperatures of 50,000 degrees Kelvin. The coolest stars have temperatures of about 3,000 degree Kelvin, and then the sun clocks in at about 5,800 Kelvin. So the sun is really a relatively cool star. Even though it has about an average luminosity compared to other stars, it's relatively cool. It's only 5,800 degrees. Okay, so other things we can tell about the star, right, is the level of ionization of materials inside the star. That's going to be related to its temperature. So let's remind ourselves what ionization means. Ionization, if I have something like a hydrogen atom, so here's a proton like this, and I have a little electron going around the hydrogen atom like this. Ionization is when you have enough energy, either in the form of the light that the star is emitting or in terms of the collisions of the atoms that are in there, to take this electron and make it so that it's no longer bound in the nucleus. And so you wind up with just a free hydrogen and a free electron. Free hydrogen proton, free hydrogen nucleus, and a free electron. That's called ionization, and that can happen for any material. If you've got carbon and you strip off a few electrons, that'll be ionized carbon. And this ionization level happens depending on temperature. So if we have a relatively cold object, most of the atoms are going to be in a solid form. If you have, as you raise the temperature, you go into steam, which is neutral gas, which is not ionized. And then when we start to get up into the tens of thousands of degrees, we have what's called a plasma. And those plasmas are basically superhot gases that have been ionized. So the level of ionization that we see in a star is also going to be related to its temperature, and that's going to become important later when we start looking at the composition of the stars. And speaking of composition, we have to talk about the folks who made this all possible. To tell a little bit of a story about where this study comes from, you have to think back to when we first started deploying the first telescopes to look at the stars. Now, this was before we had the distance measurements from the Hipparcos satellite, so all we could really measure is the color and the general spectral properties of the star. And those properties were studied by taking a giant telescope and taking the light from the telescope and putting it through a prism, and then exposing the resulting light onto a photographic plate. And those photographic plates then would be little teeny tiny spectra of all the stars, and you had to look at them with a magnifying glass. Because that was a lot of work, they had to employ a lot of people to do it. These people had to be highly educated and had to have special training. So there was a gentleman by the name of Edward Pickering, that's this crazy looking guy right here. This is Edward Pickering, and he hired a bunch of computers. And at the time, they were called computers because we didn't have computers. They were hired to compute things. Every single woman in this picture you see is a PhD astrophysicist. However, at the time, they were not allowed to be professors at Harvard where he was working, so they were hired as computers instead. However, I do want to point out that every single woman in this diagram had a PhD in astrophysics, and they were the ones who went on to make all the discoveries we're about to describe. Edward Pickering signed the paychecks and managed the payroll, but other than that, it was pretty much Annie Jump Cannon and her group of computers or calculators who did all the work. Nowadays, these women would be PhD astrophysicists and professors at the universities where they worked, but at the time, early 1900s, late 1800s, that was not a possibility. But the work that they did was spectacular, because what they did is they opened up the whole level of composition of stars, as well as classifying the physical processes that are occurring in stars. So this is a spectrum of the sun, and I want to point out, it's this nice rainbow thing that we're used to seeing, but the thing that we notice when we look very, very closely is that there are some places, like right here, where we see black lines where we're not getting any color coming through in the rainbow. So if you imagine going from red to blue, these are little strips of the spectrum. You get places where we're basically getting something blocking the light from the star. And the question is, what's blocking that light, and what are the properties of the material that's doing that? So these absorption lines are something that at the same time people were seeing them in stars, people were looking at ionized gases in the laboratory and defining emission lines from those gases that corresponded to the same wavelengths that we see in the solar spectrum. So what they discovered was that basically each molecule has its own fingerprint that you can see in the spectrum by looking at this absorption. So let's take a moment here to kind of set up the physical processes of what's going on here. So what is happening in this absorption that allows us to tell the composition of the stars? Well, let's picture a core of a hot star, right? So this is a model of a star where we have the core of a hot star right here, very, very hot, right? And then we have the atmosphere of the star that surrounds it, like this. This is the atmosphere of the star. And that atmosphere of the star is made up of stuff, right? Some sort of molecular component, right, or atomic component. We know that light is shining out from the center of the star and passing through this material. So if I have a ray of light pass through this stellar atmosphere and fly out to my telescope, I'm going to see that part of the spectrum. So this would be a little, wavelength coming out here and hitting my telescope, and I would see that part of the spectrum that would show up as a color on my spectrum. However, if there's something in this gas, like let's say a little molecule of hydrogen, that happens to absorb at exactly the right wavelength, then this wavelength of light will not be seen in my spectrum, and so I will see a dip or a block of that wavelength in my in my spectrum. So I might have another wavelength of light that isn't blocked by hydrogen that goes through just fine, right? I might have a couple wavelengths of light that do that, and then I'll see a blank spot in where I had this particular light that was blocked by the hydrogen. So how is the hydrogen blocking it? Well, the block happens because the electrons absorb the radiation that's coming from the star. So our model of a hydrogen atom is that we have a central proton in the center, and we have an electron that's in orbit around it. And this electron can only have very particular energy levels in its orbit around the proton. So if I have a hydrogen atom that looks like that, and I have a photon comes in like this that has the exact right energy to excite this electron to a higher energy state, it's going to do that. The electron's going to go up to a higher energy state in orbit around the proton, and that photon is going to get absorbed into the energy of this electron up here. Later on, that electron is going to drop down in its energy state. It'll go back down here and emit some photon like this, but it will not be in the direction of your line of sight. It will not be visible for you by the telescope that you're observing. So this is what we call an absorption situation, where I have a wavelength come in, it gets absorbed into the electron's orbit, and then later on radiates away in a different direction. The interesting thing about electrons, though, is that they can only take very, very specific energy levels as they go up and down in their orbit. So if I had a shorter wavelength of light, let's say, a blue one, if I had a shorter wavelength of light coming in, it doesn't have the right amount of energy to excite that electron, so it just sails right through, doesn't hit the electron, and goes right into your telescope. If I had a redder wavelength of light coming through, longer wavelength, doesn't get absorbed by the electron, comes straight through to your telescope. However, this green one here just has exactly the right wavelength. Whoops. Where's my green one? Has just the right wavelength, so it comes in, interacts with the electron bounces up. I do not see the green one at my telescope. So if I were to look at the rainbow here, what I would see would be some blue light and some red light, but I would not see any green light. The place where the green should show up in the spectrum is black, where I just don't see anything. Okay. So this happens again whenever you've got a hot object that's surrounded by some sort of gaseous material. So again, if I were to draw this, knowing that hot things are blue, right? Here's the core of my star. Here's the atmosphere of my star. So this stuff here is hot, surrounded by a relatively cool gas. That's going to give me absorption. And the absorption pattern you see is dependent on the materials that are in there. We have some other situations, though, that we need to be aware of, that if I just have a hot object, so this is hot, and it's not surrounded by a cooler gas, this is just called our continuous emission. And this is the thing that we see in astrophysics quite a bit, is you have these black body continuous emitters. We have them surrounded by atmospheres like in stars, but you can also have a relatively hot but diffuse object like a cloud of gas, right? That's relatively hot, but it's not dense. So it's not going to have its continuous spectrum. It's going to have a emission spectrum all by itself. So those are the three types of spectra we see. We see emission spectrum when we just have a hot gas. We see a absorption spectrum when we have a hot, dense object surrounded by a relatively cool gas. And then we have a continuous emission when you just have a hot object, a hot, dense object that's sitting there all by itself. So we're going to see examples of all of these things as we go forward and looking at this. The cool thing about it is that these two types of spectra tell us composition. because the composition is determined by the atomic materials that are in the object, and those atomic materials have specific fingerprints because of the electron structure of the atom. So the composition we can get from the emission and absorption spectrum. From the continuous emission we can get temperature. Okay. So the first thing they did when anti-jump cannon and the calculators went to look at this stuff is they started classifying these things by the strength of the hydrogen lines. They knew where hydrogen absorbed, and they classified all of the stars based on the strength of the hydrogen absorption. And the problem with that, though, is that we have this added complication with ionization, right? If you're too hot, you're going to ionize all of your hydrogen away, and you're not going to see any absorption for hydrogen because the electrons aren't there. If you're too cool, all of your hydrogen is going to be locked up in molecular hydrogen, and you won't see any absorption because you now have molecules of hydrogen instead of free atoms of hydrogen. And so classifying these things by spectral intensity of the hydrogen lines was not giving you the full picture because it ignored the temperature. So Annie-Jump Cannon and her team rearranged all of these various classifications in order of temperature. And they grouped some things together, and originally it was started out with the hydrogen lines being classified A, B, C, D, E, F, G, which was nice and in order. Turns out that was incorrect, so when they reorganized everything, they kept all of the same letter designations but just changed the order. So what we wind up with is a terribly confusing but historically accurate classification scheme, which shows that the hottest stars are classified as O stars, the coolest stars are classified as M stars, and the stars that have the strongest hydrogen lines tend to be in the middle, and that would be your A and your B lines tend to have strongest hydrogen lines because they tend to be in the middle of the temperature range. And this is the classification scheme we're stuck with because there were a bunch of people publishing, like they would say, oh, that's an A star, that's a B star, so those were all in the literature. So when they reclassified them by temperature, we had to keep the designations. So just looking at what these absorption spectra look like, here's our O, B, A, F, G, K, M stars, right? And you can see that the hydrogen lines all occur at the same spot, right? So there's this fingerprint for hydrogen. Right here you can see these dark lines, and they get strongest in the A stars because that's where they're not ionized as much, and then as we get cooler they start to go away because they're getting put into molecular states that we don't see the ionization in. You do see them in G stars a little bit there. You do see them in not so much in K, and certainly not in M. We also see other types of atoms here. Here we've got ionized calcium. Those show up in the cooler stars. Titanium oxide is a molecule that shows up in the very coolest stars. Sodium always happens at the same location. And then here's some more titanium oxide out here. So again, these fingerprints are crucial. Now if we look at the activity that we're not handing in because we needed the specialized equipment to do that activity, I just wanted to show you one of the pieces of that, which is a discussion of these, how to identify, given a full stellar spectrum, what happens to be in the atmosphere of the star. And so what we have here is three fictitious stars, and we call them star A, B, and C, although we call them ABBA, BABA, and KABA because that's a little bit more interesting names. And these are the absorption lines that we see from the stars. So let's see if I can zoom in on that. Yeah, so this is the absorption lines we see from the stars. And you can see that there's these dark lines superimposed across a gray background. That gray background is what you would see if you took a black and white picture of the spectrum. Now in my laboratory, I can put carbon, nitrogen, oxygen, xenon in controlled experiments to get emission lines. Basically make a diffuse gas that will glow at specific colors depending on the material I put in it. So this is pure carbon, and you can see these are now emission lines, but the fingerprint is the same. This is nitrogen, oxygen, xenon, hydrogen, and so forth. Because I have these laboratory experiments, I can compare to my spectrum to see what is in each star. So I can look at this and say, okay, I can ask a question like, which star has the highest abundance of nitrogen? okay, in addition to hydrogen and helium. So let's say we want the one with the largest abundance of nitrogen that also has hydrogen and helium. Well, first of all, let's make sure we see the hydrogen and helium. So here's hydrogen, right? Hydrogen has these 3 lines. So I'm going to go ahead and try to find the ones that have hydrogen. So this is my hydrogen line here, here, and here. So I'm going to go from this strong line all the way up, and I see a hydrogen line here. So this star has a hydrogen line, this star has a hydrogen line, and this star has a hydrogen line. Okay, so then we'll go to my second hydrogen line to see which one has that. This one has a hydrogen line, this one has a hydrogen line, this one has a hydrogen line, and then I go here and I should see very faintly there's a line here, here, and here. Okay, so all of these stars have hydrogen, every single one of them. If I look at helium, again, I want to look at for patterns here. I'm going to start with the strongest line, go up here. There's a helium line right here, helium line right here, and a helium line right here. And then I look at this doublet. We call that a doublet because they're easy to find. There's a doublet here. There's a doublet here, and probably in there someplace, although it's hard to tell because there's a lot of other stuff going on there. But there's more than likely some hydrogen going on in there as well, this doublet, since we have these other helium lines as well. So all the stars have hydrogen and helium. So the question was, which one has nitrogen, right? So I go and look at this. Here's my nitrogen spectrum, and I try to find some distinctive feature that shows up in all of these lines in one of these spectra. So I'm going to start with the brightest lines here. There's this cluster of 3, which looks pretty identifiable. So let's go check that out. Well, I don't see anything here, and I don't see that pattern here, but I definitely see that pattern right here. So we know that this one has to have a higher abundance of nitrogen than those other ones. Now, it doesn't mean there's no hydrogen in the other stars. It just means that there's not enough for us to detect. And just to double check, I can find another triplet over here, and yep, sure enough, that shows up right there. And if I look over here, here's another blob of emission lines, and that very same pattern shows up right here. So we can tell that that one has nitrogen in it. You can go on further and ask things like, well, which one has the most carbon? Well, let's take a look at this guy right here. This is a very strong carbon line. I definitely see that here. I don't see so much of the strength of the carbon here. So I'd have to kind of put a question mark and say, well, is this carbon or not? I'm not quite sure, but it's certainly not as strong as this one, so this one has the most carbon. And again, to double check, I'd go try to find these lines. Oh, there's those lines there. Oh, I don't see anything there, so there's no carbon in this one. There is carbon in this one. And then lastly, if I look at this star, I could try to find the one that has oxygen in it. Again, I go to oxygen, find the fingerprint. I don't see those here or here. I do see it here and here, so this is the one that has the oxygen in it. So we can tell the composition of the stars just by looking at them, and the strength of the absorption lines are going to tell you how much of the material is there once you factor into the fact that the temperature controls the ionization. So it's entirely possible, and more than likely, that this star right here has some carbon and oxygen in it, but it's just ionized in a form that it can't be seen. But it's a very powerful tool to be able to figure out the composition of stars just by looking at the spectrum. And the only reason we can do that is because in the laboratory I can make detailed measurements of emission spectra, and I can compare that to detailed observations of absorption spectra in stars and compare the two fingerprints and get the combination of materials. Okay, let's go back to our presentation here. Okay, the last thing that we can want to know about these stars is their mass, and that mass is something that is very difficult to measure because we can't just weigh these objects. What we have to rely on is some of these stars have to exist in multiple binary pairs that orbit one another. And if that's the case, we can determine their mass by watching their motion. If they're not orbiting anything, we can't tell their mass. Luckily, a number of stars in our sample do have companions that allow us to measure the mass. This is very similar to what you did with dropping marbles to measure the mass of the Earth. you use the motion of the stars to determine the gravitational acceleration, and you can get their mass. And we find that the hottest stars have masses that can be up to 100 times a solar mass, and the least massive stars can be about 100th of a solar mass. And again, that puts the sun kind of in the middle of the range for mass. So that's another reason why we might say the sun is an average star, because it's kind of in the middle range for mass. Okay, before I move on to the Hertzsprung-Russell diagram, I want to show you one thing, and that is a movie of star formation, because we want to see how these stars form. So what you're seeing here is a cloud of dust and gas that is, when I hit play, is going to start reacting gravitationally. It will begin to collapse, and you'll see what happens when we do that. Now, you can see the distances up here. We have dimensions of about 82,000 astronomical units. Remember, Pluto's orbit is about 40 astronomical units, so that gives you some perspective of how big this cloud is. And you can also watch the time up here. So the time is going to tell you how long this takes, and I think you'll be surprised at how quickly this goes. The color is telling you the density of the gas. So here we go. So immediately the cloud starts to fragment because of gravitational collapse, and the dust and gas in this cloud condenses into cores, which are eventually going to form stars. And you can see here we're going to rotate this around, change the scale a little bit. Let this evolve a little bit more. You can start to see that the cloud is beginning to collapse into various objects that will ultimately be stars. But it's pretty complicated. It's not as simple as just a cloud of gas collapse into a star. Here you can see tertiary companions, quadruple companions. We've got 5 or 6 stars orbiting one another. Here's going to be a close collision of a bunch of stars. We see these things scattering around. Here's one with a disk. Right here, I don't know if you can see this one, it's got a nice disk of material around it. That's going to form a star system here. These don't have very prominent disks, which is interesting. Here's a nice swirling pattern down here. So again, a very complex process for this stellar formation. But again, it also illustrates how we might be able to find star systems with multiple stars so that we can determine the mass of these objects. Some of these star clusters can be pretty dense and have lots of stars close in. Some of them get scattered out. Our sun was born in a star cluster where we probably got scattered out at some point. And then this is the result, something that looks like a star cluster, which we'll explore a little bit later next time. So that gives you an idea of how quickly this star formation happens, and the dimension on which it happens, and also the time. You can see that only 266,000 years have passed for these stars to initiate their formation, which is pretty impressive. The problem we face with astronomy is that there are all these stars out there, and they live for billions of years, and we can't just watch them evolve over time. We have to take a snapshot in time and see if we can figure out their entire billion-year life cycle by just looking at all the different statistical properties of all these stars. So we'll play a little game here. We're going to do some anthropology. I like to call the HR diagram effectively stellar anthropology, because what we're doing is taking a snapshot in time of a life process that exists over many, many more years than we can observe. And so if you were an alien visiting the Earth for one day, right, and you had to figure out these crazy humans and figure out what their life cycle looked like, you would have to make some key observations that you could only do in one day. You couldn't wait to watch people live and die, and you'd have to make this model from just observations, because you don't want to disturb the people. You don't want to abduct people and study their biology. So you just want to go and observe the properties of humans to see if you can figure out their life cycles. So the first thing you'd ask is, well, where do you want to observe and where will you go, right? So I have a couple of examples of what you might want to observe. In terms of what you might want to observe, well, we don't know anything about human physiology, so we just look at the humans and we know that some of them are bigger than others and some of them are smoother than others. If you look at some of the humans you see don't have any wrinkles, and some of them have a lot of wrinkles. And so these are easily observable properties that you can tell just by looking, right? So you can just measure their height or measure their wrinkliness. So this is the diagram we're going to construct here. So the first place we're going to go is a nursery. We sneak into a nursery and take a look at all of these human little things here. These are types of humans that we see. And we pick a nursery because it's a place where one type of human is very easily observable. And we see a bunch of humans that are small, they're short, and they're smooth, relatively smooth. So when we make our diagram, we put those guys over here in the less wrinkly small categories. So we have a class of objects over here. We could call these the smooth type humans, because we don't know anything about their physiology. We just know there are some smooth type humans over there. Okay, then we go visit someplace else. We could go to a retirement home, and we find a bunch of other types of humans that all seem to be alike. They have wrinkly skin. They happen to be roughly the same height. There are a few outliers, like this gentleman right here. Right, this gentleman is clearly not as wrinkly as the others, but you've got some wrinkly type humans that all happen to be of roughly the same size. So that gives me another class of objects, which I could call the wrinkly type humans that are over here on this side. Right? So I'm starting to see different classes of human beings show up on this diagram. Now I would like to get a more universal sample, so I pick a couple of other places to go. I could go to the mall. Seems to be all the huge diversity of people that are at the mall, and I plot them on my graph, and I get another cluster of humans that is something like right here. I don't see a lot of babies, maybe one or two. I don't see a lot of the wrinkly ones, but I see some of these what we would call maybe main type humans that are in there. And then I might go to a football game. Right? A football game is interesting because it has a wide cross-section of spectators, but it also has some very unique participants who happen to be maybe a little bit taller, maybe a little bit younger than we might expect from what we've seen, so they're a little bit less wrinkly, and I would get a distribution from the sports game that looks like this. I might have some outliers here where I have some folks who are really tall but not so wrinkly. Okay. So I've constructed this diagram based on two arbitrary properties that are easy to observe that is clearly telling me something about the life cycle of human beings. And I can even start to classify them. I can have my main type humans, right? I can have my rough type humans, and I can have my smooth type humans. And looking at the fact that there is kind of a separation between these things, there could be and should be some relationship between these different groups. And I can start to draw some conclusions. I could say, make a hypothesis that says that, well, my smooth type humans, all of the humans start out here, right? And then they get a little bit more wrinkly, and they get a little bit taller over time, and then they wind up in the main type. And they spend most of their time at one spot in the main type because you tend to be about the same height and the same wrinkliness over time. Then as you get a little bit further along in your life cycle, you get a little bit more wrinkly, right? You might shrink a little bit because you're getting a little less tall, and you wind up over here in the rough types humans. So there's smooth type humans are the progenitors, rough type humans are the results of human evolution, or at least human life cycle, and the main type humans is where most humans spend their time. And this is a conclusion that aliens could draw by doing this type of analysis. Well, we do the exact same thing with the HR diagram. Now, Hertzsprung and Russell, at the time that the HR diagram came out, were working on this independently, and they knew that we had measured two properties of stars. We had measured their luminosity, and we had measured their temperature. And these were two fundamental properties of stars that were measured for a huge collection of stars, and they decided to just make a graph of plotting one against the other. And this is the diagram that results. This is the Hertzsprung-Russell diagram, which has temperature going from cool to hot on the bottom, and that's the reason for that is because the way that they measured the wavelengths and the colors of the stars was inversely related to their temperature, but we wind up with the temperature going from cool to hot, right to left, and then luminosity goes higher on the y-axis as you go up. Right here, this is one solar luminosity, and the sun is 58 degrees Kelvin, so we can plot the sun on here. There's the sun at 58 degrees Kelvin and one solar luminosity. Stars going up this side are hotter and tend to be younger. Stars going down this side are cooler and can be much older, and they're much less massive. And we're gonna not worry about these guys just yet. We're gonna talk about those a little bit later when we talk about stellar death. So let's just look at the main sequence here, which is this material, these stars right down here in the middle. So the main sequence is telling us something about the main life cycle of the stars. Now, a star, when it achieves its form through this process of gravitational collapse, it begins to fuse hydrogen into helium, and it obtains its spot on the HR diagram, just like a human would once it attains its full height and its relatively normal amount of wrinkliness. It winds up on this diagram. So the sun, for example, is right here, and the sun is on, oh, that's not the sun. The sun is right here. Here's the sun. The sun is right here at 1 solar mass, 1 solar luminosity, 5,800 degrees, and its lifetime on the main sequence is about 10 to the 10 years. And we know that just because we know how much mass is in the star and we know how bright it is, and since we're converting mass into energy, you can calculate the lifetime from that. As you go further up on, oh, go ahead. You got a question, Shane?
John, you're saying that all these stars go through a life cycle? Is that what you're saying?
Yeah. So what they do, and we're going to talk about the end result a little bit later. But when these stars are formed, depending on their mass, that determines their brightness, and their brightness determines their temperature, and that puts them someplace on the main sequence. And that's where they're fusing hydrogen into helium as their main power source until they run out of fuel. Now, once they run out of fuel, then they're going to die and fall off the main sequence and become another type of object, which we'll talk about a little bit later. But while they're on the main sequence, they're fusing hydrogen into helium, and they will pretty much stay that same in that same position. But yeah, they have a life cycle, and the life cycle is determined by the amount of fuel they have, and the amount of fuel they have is determined by their mass.
So they're not all going to be blue in the beginning and then end up red.
No. Yeah, no, they're not. What you're going to have is, so that simulation I showed you, you saw some of the stars were brighter than others that formed. So the dim stars, when they form, the ones that form with low mass are going to form down here, right? The ones that have a lot of mass are going to form up here. And that's where they're going to be, right? They're going to be on this main sequence for the lifetime that's indicated here. And in fact, these red stars can effectively live longer than the age of the universe. So there could be red stars that were formed near early on in the universe that are still around. Our sun is going to live for about 10 to the 10 years. Now, I like to call this the rock star theory of star formation because the bright stars burn fast and die young. So they're like Jimi Hendrix. And the cool stars are like Donny Osmond. Right? Because they're they fine musician, but he's just tootling along there. But this is your Kurt Cobain, your Jimi Hendrix, or whatever up here. But so these blue stars, the reason that they live so short, right? I mean, look at this. This is 10 to the 7 years. So this is 10 million years up here. Okay, 10 million years compared to 10 billion years down here. So in other words, these stars, we could go through 6 of these stars since the dinosaurs went extinct? That's crazy. These things live a very short period of time. But the reason for that is because they're so incredibly bright. They're 30, 40, I'm sorry, they're like, what is this, 10, they're up to 1 million times as bright as the sun. So they have more fuel. Yeah, they're more massive. They might have 30 solar masses, but they're burning it at 1 million times faster. So they just burn through their fuel really quick. What's that?
I was going to say they're burning it faster then.
Yep. So it's kind of like if you have an SUV with a large fuel tank, you're still only going to be able to go 300 miles because your fuel economy is so low, right? Because the engine's so much more powerful. Yep. Even though you've got more fuel. Okay. So that's our main sequence. The stars, as we get more massive along the main sequence, they get larger radii. So these are going to have the large radius stars are going to tend to be on the upper part of the diagram, and the small stars are going to be on the lower part of the diagram. And if we find stars up here, we call them giants or supergiants, and those are evolved stars, which we'll talk about a little bit later. And small radius stars tend to be down on this bottom part of the chart, and if we find small stars in this area down here, they tend to be white dwarfs. Again, we'll talk about those when we talk about the life and death of stars. Just to complete our classification scheme, though, we have our spectral sequence, right, which is this right here. The spectral sequence is this, which is our OBAFGKM, right? So we can say, if you go look up in the literature and you find a G-class star, that means that's going to be a star that's like the sun. If you find an O-class star, that's going to be a star like this. If you're on the main sequence, we use the Roman numeral 5 to indicate the main sequence. And if you happen to be above or below the main sequence, we give you other Roman numerals 1, 2, 3, or 4. This is just some common star designations that you might see. Okay, so I think I'm going to stop there because we're going to get to, on our next time, we're going to talk a little bit about star clusters and how we can use this information to get things like the ages of stars and the distances to stars by looking at star clusters. So I just want to stop there and see if there are any questions on the basic HR diagram.